Hi, my name is Vasilis Sarafidis. I am Professor of Finance at Brunel University, London, and today I would like to present you a method designed to test the so-called run condition for the Common Correlated Effects estimator. This estimator was proposed by Pesaran in 2006 for heterogeneous panel data models with latent common factors. I would like to thank Jan Ditchen for incorporating our method as an option into his powerful Stata command xtdcce2. The first part of my presentation will focus on the method itself and how it works, while the second part of the presentation will illustrate the method in Stata and discuss different aspects of implementation. So the model of interest is given by equation 1. Y I is a vector of order t, which collects all observations on the dependent variable over time for individual I. And on the right-hand side, xi is a t by k matrix of covariates, while u is a composite error term, which consists of a latent common factor component and a purely idiosyncratic error term, epsilon. So F here is a t by a matrix of latent factors that hit the population of all individuals, albeit with different intensities, as reflected by the individual specific factor loadings. Without loss of generality, I will assume that the slope coefficients beta are the same for all individuals. This is only to simplify the exposition, as it does not really affect how our methods work. Now, if X is strictly exogenous with respect to the composite error U, then one can estimate beta consistently using standard least squares or pooled least squares. A more relevant setup from the empirical point of view is to allow X to be correlated with a common factor component, in which case neither pooled least squares nor the within or fixed effects estimators are going to be consistent anymore. The reason for the latter is that the fixed or the within transformation does not eliminate the factor component from the error. Now, to ensure that X is correlated with a common factor, Pesaran 2006 assumes that X is also hit by the same factors F with loadings given by gamma I. So effectively, it is assumed that the stochastic process for X can be decomposed into a common factor component with the same F as in equation 1 and a purely idiosyncratic error given by V. Now replacing X for what X is equal to in equation 1 and stacking Y and X together yields the following T by K plus 1 matrix of observables given by Zi. So essentially, we have expressed all the observables, both Y and X, solely as a function of a common factor component and pure noise. Now, the key idea behind CCE is to control for the unobserved F using cross-sectional averages of Z. In particular, taking sample averages over I yields the following equation in terms of Z bar. So Z bar denotes the sample average of Zi. And now post-multiplying left and right-hand sides of equation 4 by this quantity here implies that we can actually use the resulting expression here in equation 5 to solve in terms of F. So under certain regularity conditions, as n grows large, this quantity here converges in probability to F, while this quantity is asymptotically negligible. So effectively, what we have shown here is that F is spanned by linear combinations of Z bar. So although we do not directly observe F, we can control for F using cross-sectional averages of the observables. A fundamental requirement here is that C bar, which is of order m by k plus 1, has full column rank. Otherwise, the inverse of this matrix does not even exist. So the inverse of the outer product between C bar with itself does not exist. And therefore, we cannot really use these equations anymore to solve in terms of F. Now, the requirement that C has full column rank, C is the population counterpart of C bar, is the so-called run condition for the CCE estimator. And when the run condition fails, the CCE estimator is no longer consistent in general. For this reason, it is highly important to be able to check whether the run condition holds true for any given sample. Now, the run condition can be expressed as follows here. So the rank of C equals M. That's the first condition. And the second condition is that M is less than or equal to K plus 1. When the run condition fails, as we said before, CCE is no longer consistent. The question now is, when does the run condition fail? Well, the most obvious example is when the number of factors is larger than the number of observables. In that case, we do not have enough information to control for F. However, even if M is less than or equal to the number of observables, the run condition might still fail. One case occurs when some columns in X do not really load on F. That is, some columns in gamma are 0. Secondly, it is also possible that although the columns in X do load on F, it turns out that the factor loadings average out. So when we take averages, when we compute Z bar, the factor loadings average out. Thirdly, it is also possible that some columns in X might not contain information that is distinct from that already provided by other variables. In all these cases, the CCE estimator is not going to be consistent. Now, in principle, if we knew what rho is the rank of C, and we also knew what M is, where M denotes the number of unobserved factors, then we could directly check whether the rank condition holds true or not by comparing these two quantities. Now, while there exist several methods in the literature for estimating M, estimating rho is not really that obvious. And the reason is that rho is a rank of C, which is the population average of the factor loadings. And therefore, since C is unobserved, rho cannot be directly evaluated. For this reason, to date, the rank condition has been taken pretty much for granted, even if it is absolutely crucial for the properties of CCE. Now, a key insight in our paper is this. Noting that Z bar is a square root n consistent estimator for FC for any fixed t, then it follows from this rank equivalence result, which requires that F is full column rank to begin with, but that is a standard assumption even with principal components. So it turns out that rho can be consistently estimated by estimating the rank of Z bar. Therefore, given that rho and M can be estimated consistently, we put forward the following binary classifier. So here, this is an indicator function which takes the value of 1 when the statement inside the curly brackets holds true and 0 otherwise. So when the estimated rank of C is less than the estimated number of factors, then this term equals 1, 1 minus 1 equals 0, so the rank classifier equals 0. On the other hand, when this argument is not true, the rank classifier equals 1, so the rank condition is deemed to be satisfied. So the question now is, how do we really estimate rho, the rank of Z bar? And what are the resulting properties of the binary classifier? There are several methods in the literature available for estimating the rank of a random matrix. In our paper, we have adopted the sequential testing procedure proposed by Robben and Smith in 2000. The reason is that this procedure is pretty easy to implement, and it relies on relatively mild assumptions. In particular, unlike other methods, this one does not require the variance-covariance of the estimator of the unknown matrix FC to be full rank, or its rank to be known. So in principle, the rank of Z bar can be estimated for any fixed t by testing sequentially the null hypothesis that rho equals rho star against the alternative that rho is larger than rho star, using this statistic here, where the lambdas are the ordered eigenvalues of the n by n matrix A, the outer product of Z bar with itself. Now notice that for this method to work, one requires that the dimensions of Z bar are fixed. Now clearly in our setup, this assumption will be violated, of course, when t is large, because Z bar is of order t by k plus 1, and therefore the number of rows in Z bar actually grows together with the sample size. So to circumvent this issue, we introduce a so-called narrow n by t matrix psi, such that the product between psi and Z bar is n by n, and n is fixed. So in the most basic example, n is simply equal to k plus 1. Now the question is, what choices of psi there exist? So one choice of psi is to simply take psi to be a random matrix with IID standard normal entries. In that case, theorem 1 of our paper shows that the probability that the rank of psi times FC equals the rank of FC itself is 1 for n sufficiently large. Another choice for psi is simply to take averages over every nth row in Z bar, and we can achieve that by setting psi equal to this expression. This is a so-called fold-over matrix. Finally, one can also set psi equal to this expression here, which essentially makes use of only the last n rows of Z bar to estimate the rank. Notice that both of these choices are deterministic. Now, the first two choices, so this choice here and this one here, the fold-over matrix, have actually been implemented by Jan Ditzen in his XTDCC2 command, and the default option is this one here. Okay, so I think this is a good point to move over to the state illustration using the XTDCC2 command.